Hello everyone, this is a continuation of the previous lecture, and in this lecture we will see how to obtain fully secure blockwise fully secure MAC from blockwise prefix free secure MAC, and then eventually we will see how to obtain fully secure MACs for arbitrary long bit strings. So, now let us discuss the other approaches, how to convert a blockwise prefix free CBC PRF to a fully secure blockwise PRF, right, and this will be through some encoding. And the basic idea here is that what we do is we apply some publicly known encoding function to the message space of the blockwise prefix free PRF, so that the encoded message space constitutes now a prefix free message space. And what basically it means is that imagine you have a message space for the prefix free PRF consisting of up to L blocks or each of size n, L minus 1 blocks each of size n bits. What we will do is we will apply some mapping or encoding function which I denote as PF, and the encoded message space will now consist of a sequence of block up to little l blocks each of size n bits. And the way mapping is done here is as follows. So, right now we are actually considering a deterministic encoding mechanism. Later on we will consider a randomized encoding mechanism as well. So, the way this deterministic encoding mechanism works is as follows. So, all the input blocks say you have a sequence of input blocks A. So, the corresponding encoded input A will be as follows. So, all the message blocks of A are copied as it is in the encoded output, and apart from that we now introduce an additional block here, namely the binary representation of the number of blocks in your input A. So, that is the notation, this within the angle brackets you have the binary representation B, right. So, that is why you can see that the input space could consist of up to L minus 1 blocks, and since we are now introducing an additional blocks in the encoded output, that is why the outputs now can consist of up to little l blocks. We have an additional block here introduced because of the encoding process. And the idea here is that using this deterministic encoding process, we hope that instead of operating the prefix free CBC PRF over the message space, we are now going to operate it over the encoded message space. And since the encoded message space will constitute a prefix free set, our distinguisher cannot issue queries which will constitute a prefix free set, and hence the overall construction will be a fully secure PRF. So, now let us prove that the deterministic encoding which we have seen here indeed constitutes a prefix free mapping. That means, the mapping from the message space, which could be a non prefix free set, to the encoded set gives you an encoded set which actually constitutes a prefix free set. That is what we want to prove. So, first of all, it is easy to see that the mapping is injective, or namely 1 to 1. That means, if you have two inputs M1 and M2 consisting of sequence of blocks say up to little l minus 1 blocks, and if we encode them, then they are going to be different if M1 and M2 are different, because if M1 and M2 are different, then definitely the blocks which are present in M1 and blocks which are present in M2 will also carry over in the encoded M1 and in the encoded M2, and they will be differing, and hence the encoded M1 and encoded M2 will be different. So, that proves that your mapping that we have defined here is indeed a 1 to 1 mapping, right. Now, we want to prove that the image set of PF, namely all the encoded messages that we get as per this mapping, constitutes a prefix free set. So, imagine you have two inputs belonging to the message space, say the input sequence A and another input sequence B consisting of V and U number of blocks, and say A and B are different inputs, right. So, my claim is that the encoded input A and the encoded input B are not proper prefix of each other. And if we prove this for an arbitrary input A and an arbitrary input B, that proves that the encoded it proves that the mapping that we have considered indeed gives you a prefix free set. So, clearly the claim that we are making about the encoded A and encoded B is true if the number of blocks in A and the number of blocks in B are same, namely if U and V are same, but if A and B are different, then definitely at least one of the blocks in the encoded A and the encoded B will be different, because all the blocks in A and all the blocks in B cannot be same even if A and B are different. So, the claim is trivially true if U is equal to B, U is equal to V, whereas if U is not equal to V, that means if the number of blocks in A and the number of blocks in B are not same, and still if A is not equal to V, A is not equal to B, then definitely the binary representation of the number of blocks in A and the binary representation of the number of blocks in B will be different. That means the first block which we are actually putting in the encoded A and the first block which we are putting in the encoded B will be different, which will ensure that overall the encoded A and the encoded B are different. So, that proves our claim that the image set of the mapping that we have considered here indeed gives you a prefix free set, right. So, now let us see how we apply this prefix free encoding and to a prefix free secure CBC blockwise secure PRF and get a fully secure blockwise PRF, right. So, our goal is to construct a blockwise fully secure PRF taking n bit key and a sequence of blocks as input up to L minus 1 blocks, each of size little n bits, and to obtain a fixed size output of size little n bits. And for demonstration, assume that we want to operate this blockwise fully secure CBC PRF on an input consisting of say 2 blocks M1 and M2. So, what we will do is that we will first convert this input M by applying our deterministic prefix free encoding, namely this message M is converted into an encoded input, and when we convert it in an encoded input, then the message blocks are repeated as it is, and apart from that at the beginning we now have a new block, namely the binary representation of the number of blocks that are there in M, right. So, now we have one more block compared to the number of blocks which are present in M, and once we have the encoded input, what we do is we apply the existing construction, namely the blockwise prefix free secure CBC with the key of size n bits, and the output will be considered as the output of the blockwise fully secure CBC for the message M under the key K, right. Now, why this construction is intuitively secure? Because now even if an adversary is asking, even if the adversary asks for the function output on a input A1 and on an input A1 comma A2, actually he will be getting the output of the function on the input sequence A1 concatenated with A1 and the output sequence he will get the output of the function on this input and he will get an output on this sequence, right. And hence he cannot launch the attack that we had seen when we discussed the insecurity of the blockwise prefix free secure PRF, because even now he is making queries which constitute a prefix free set. Basically those queries are converted into another set of queries which is not a prefix free set, and from the viewpoint of an adversary is now as good as he is interacting with a normal PRF. So, that is the overall idea of the security proof, but the formal details are indeed advanced in nature, and that is why I am skipping the details here. So, if we see the advantage of this construction, namely this way of constructing blockwise fully secure PRF via deterministic encoding, then the advantage is that we need only one key, unlike the encrypted CBC PRF where we need to operate with 2 keys. However, the disadvantages are as follows, right. So, we need an additional PRF invocation, right, for this additional block which we are introducing here. Ideally, we expect a PRF where the number of base PRF invocations are same as the number of blocks in the message, but actually in this overall construction we need to have one additional invocation of the base PRF. And bad news about this construction is that it no longer constitutes a streaming MAC, because the length of the message or the number of blocks in the message need to be known in advance to the sender, because if the number of blocks in the message is not known to the sender in advance, then the encoding of the message cannot happen, because the encoding requires the binary representation of the number of blocks in the message that is present, which has to be inserted at the beginning. So, that is why it does not gives you a streaming MAC, right. So, that is the approach of going from block-wise prefix-free secure PRF to a block-wise fully secure PRF using deterministic encoding. And now we see how we can go from this block-wise prefix-free secure PRF to block-wise fully secure PRF using a randomized encoding, a randomized prefix-free encoding. So, the reason we want to go for a randomized prefix-free encoding is that the problems that we face with the deterministic prefix-free encoding is that we do not get a streaming MAC and we need to have an additional invocation of the base PRF. And the solution to get around these two problems is to use a randomized prefix-free encoding, which will be a keyed encoding. And the way we do the encoding is as follows. So, we first introduce some notations here. So, imagine you have two block sequence inputs, say input x and input y, each consisting of up to L blocks, each of size n bits. Then we, if x is a prefix of y or if y is a prefix of x, then we use the notation x is related to y by this notation, by this symbol, right. So, now we introduce the definition of what we call as randomized epsilon prefix free encoding, where epsilon is some parameter, and what this encoding does is it takes as input a key of size say little n bits and a block sequence of consisting of up to little l blocks, and it gives you an encoded output which is a keyed encoded output for the input A. And when I say that it is a randomized epsilon pre-encoding, what it means is that the probability that you obtain two inputs A and B from the domain input domain consisting of up to little l blocks, such that under the same key k the corresponding encoded outputs are related to each other by this prefix relation is upper bounded by epsilon. That means, if you have one sequence A and if you have another sequence B, then the chance that the encoded A and the encoded B is prefix of each other, or the encoded A is a prefix of encoded B, or the encoded B is a prefix of encoded A, is upper bounded by epsilon. That is what I mean when I say that I have a randomized epsilon free encoding. So, basically the idea here is that we want to the idea here is that if there is an adversary or computationally bounded adversary, and if it does not know the value of the key k with which we are actually doing the encoding, then for the adversary it is very difficult to come up with a pair of inputs A comma B consisting of up to little l blocks, such that either the encoded A is a prefix of encoded B or the encoded B is a prefix of encoded A. That is what is the requirement from that is what is the security requirement from this randomized epsilon free encoding. I stress here that the mapping or the randomized and the way this randomized encoding is operated, it is not necessary that the mapping should be an injective mapping. That means, you can have multiple A's whose encoding will be the same under the key k, but the security guarantee that we obtain from this epsilon prefix free encoding is that even though there could be several such candidate A's which under the key k would have given you the same encoded output, the probability of finding such multiple A's in polynomial time should be upper bounded by some negligible quantity or by the quantity epsilon. I also stress that unlike the deterministic prefix free encoding, the encoding that we are constructing here, namely the keyed encoding, it need not give you a prefix free set. However, even if it is not going to give you a prefix free set, the chance that adversary could come up with that pair of input A comma B such that encoded A is a prefix of encoded B or vice versa should be upper bounded by the probability epsilon. And if we ensure that epsilon is very, very small, then we are done, right. So, now assume for the moment you have okay. So, what we are going to now do is we are going to define a randomized epsilon prefix free encoding for our CBC PRF, right. And the way we define this encoding is as follows. So, imagine you have an input consisting of several blocks, say u number of blocks, where u is upper bounded by little l and each block is of size n bits, and we have a key with which we want to do the encoding, right. So, the encoded output A will be as follows. You repeat all the blocks of A except the last block, and the last block is basically the XOR of the last block of the actual A and the key k. So, that is how we are actually computing the encoded A. And my claim is that if the key for this encoding is selected uniformly randomly from the set of little n bit strings, then this mapping constitutes a 1 over 2 to the power n prefix free encoding. That means the probability that an adversary who does not know the value of k can come up with two inputs A and B such that either the encoded A is a prefix of encoded B or vice versa is upper bounded by probability 1 over 2 power n, which is definitely a negligible function in the security parameter, right. So, let us prove that. So, imagine you have a block, you have an input a block sequence A and another input B, a sequence of blocks, and say A and B are different, right. And we want to find out what are the chances that the encoded A and encoded B, either the encoded A is a prefix of encoded B or vice versa. So, first of all, notice that if the number of blocks in A and the number of blocks in B are same, and if A is not equal to B, then for every value of the key, definitely neither the encoded A will be a prefix of encoded B or vice versa, because when we do the encoding, right, all the blocks of A except the last block and all the blocks of B except the last block will be present in the respected encoded outputs, and the last block will be the XOR with respect to the key. So, definitely all of them will be different, neither will be prefix of each other. On the other hand, consider a scenario where, say, without loss of generality, that the number of blocks in A is less than the number of blocks in B and A is not equal to B. Then what is the probability that encoded A is a prefix of encoded B? Well, encoded A will be a prefix of encoded B if and only if the following relationship holds. Namely, the last block of the encoded A will be this, the XOR of the key with the last block of A. Whereas the uth block, right, I am assuming here is u is less than b. So, the uth block of the encoded B will be bu, right. There will not be any operation with respect to k, because there are many more number of blocks in the input B which are still available, because we are in the case where u is less than b. So, only if this relation, namely the XOR of AU and K and BU, if they are same, we can hope that the encoded A will be a prefix of encoded B. But this holds only if the value of key which is selected for doing the encoding is actually the XOR of the last block of A and the uth block of B. And since the key for the encoding is chosen randomly from the set of little n bit strings, the probability that indeed key satisfies this relationship is 1 over 2 power n. That means this encoding that we have seen is a very simple encoding, but it has a very powerful property that it gives you a 1 over 2 to the power n prefix free encoding, namely an adversary, a computationally bounded adversary who does not know the value of the random key k. It cannot come up with a bad pair of inputs A and B such that either the encoded A is a prefix of encoded B or vice versa. So, now let us see that how by using this randomized prefix free encoding we can convert blockwise prefix free secure PRF to a blockwise fully secure PRF, and the idea is the same. Instead of as we used for the case of deterministic encoding, right. The only difference is that instead of applying the deterministic encoding, we are going to apply the randomized encoding. So, now we will be operating with two keys, each of size little n bits. So, that is why the overall key for the full blockwise fully secure CBC will be of size 2n bits, and it can support a sequence of blocks consisting of up to little l blocks, where each block is of size little n bits, and it will give you a fixed size output. For demonstration, assume that we have a message consisting of up to 3 blocks. So, what we do is the overall key for the CBC PRF is interpreted as 2 chunks of little n bit keys. So, the first part is denoted as K1, and with K1 we first do the encoding of the input, namely the message M is encoded as per the key K1 via the randomized prefix free encoding, and the size of the encoded output and the size of the input remains the same. That is important here, right. This is in contrast to the deterministic prefix free encoding, where the encoded output consists of one more block compared to the number of blocks present in the input. And once we have the encoded input, we now apply the blockwise prefix free secure PRF with the second part of the key, right. So, that is why we need 2 keys, one for doing the randomized encoding and one for doing the actual PRF computation. And whatever output we obtain from the block-wise prefix-free secure PRF, that is considered as the overall outcome of the block-wise fully secure PRF under the key K1, K2 for the message sequence M. Now, intuitively why this construction is secure? Because what we have done is, with very high probability, we have actually converted the input set of this CBC PRF into a prefix free encoded set, right. Even though it is not in principle a prefix free encoded set, the probability that an adversary without the knowledge of key K1 could come up with a bat pair of inputs M and M dash, such that the encoded M is a prefix of encoded M dash or vice versa can happen, is very negligible, and that ensures that overall construction looks like a normal PRF construction. The advantages of this way of constructing a block wise fully secure PRF is that we do not need the length of the message to be known in advance at the sender end, right. That is why we obtain now a streaming MAC or a streaming PRF, and we do not need any additional base PRF invocations. So, we get rid of both the shortcomings that were there when we were using a deterministic prefix free encoding. It was not giving us a streaming MAC, and we need to have one additional PRF invocation because the deterministic prefix free encoding requires one additional block in the encoded output, but that is not the case here. However, you need to pay a price here. The disadvantage is here is that you now need to operate with 2 keys, whereas if we see the deterministic prefix free encoding, we were operating only with 1 key. So, now you have a trade off. Okay. So, now let us see how we go from constructing bitwise fully secure PRF from blockwise fully secure PRF. So, remember that our final goal is to construct a PRF or a message authentication code which can take a sequence of bits as input. So, till now the PRF or the MAC that we have constructed could take only blocks or sequence of blocks as inputs. So, the idea behind constructing a PRF which operates on a sequence of bit is that you first apply some unambiguous padding depending upon whether the input bit string which you want to feed as an input to your PRF is a multiple of the block size of the base PRF or not. So, for simplicity assume that the block size of the base PRF is little n bits. Now, you want to design a PRF which I denote as F star CBC taking a key of size n bits, and it can take any input bit sequence of length up to NL bits, right. And now there could be 2 possible cases depending upon whether the input for this PRF F star its size is equal to some multiple of n or not. So, remember I am assuming that the block size of my base PRF is n bits. So, case 1 could be when the input size m is some constant times n, and the case 2 could be when the size of the input is not equal to any constant times m, that means it is not a multiple of n. So, depending upon 2 cases we operate the so called PRF F star that we are interested to construct in 2 different ways. So, let us take case 1. In both the cases we have to do a padding. So, what we do in case 1, so for instance imagine my message that I want to input here is of size 2 n bits, that means I can divide it into 2 blocks of n bits, n bits, n bits. And now I have to do an unambiguous padding. So, in this case actually I do not need to do a padding because my message is already a multiple of n bits, but to indicate it to the receiver that actually I do not need to do a padding, what I am going to do here is I am going to add a dummy block consisting of n bits starting with 1 followed by all zeros. So, that is an indication from the sender side that actually I am not doing any padding. Now, to operate F star in this case what we are going to do is we are going to take a key K1 which we will soon see how exactly is computed. So, remember that the key overall key for F star is just one key of size n bits, but what we are going to do is we are going to derive several sub keys, and depending upon whether we are in case 1 and case 2 we are going to use some subsets of those sub keys. So, in this case we use a sub key which I call as k sub 1, and then what we are going to do here is we are going to operate our blockwise fully secure CBC PRF with 2 keys each of size n bits, and since it is a blockwise fully secure PRF it can take a sequence of blocks of n bits up to L plus 1 such blocks. And sorry for the rendering issue here, this 0 comma 1 raised to power n should be here, and it gives you an fixed output. So, if you see the outer view of the PRF F star that we are going to construct here, it could take an input of size NL bits, right. And in this case, if my input already is a multiple of n, that means it could have up to L number of blocks. But if you see the inner invocation of the blockwise fully secure PRF, then it could take up to L plus 1 blocks of size little n bits. Now, you might be wondering that why this additional 1 block? This additional 1 block might come if actually your message is already a multiple of n, in which case you need to add a full dummy new block of n bits. So, that is why the inner invocation of my blockwise fully secure PRF could take up to L plus 1 blocks. So, internally what I do is I operate my blockwise fully secure PRF, and for doing that actually I first take the message, the padded message, and I apply a prefix-free randomized encoding with the sub key k1, and then I use another sub key k0. Again we will see soon how exactly the sub keys k1, k0 are derived. So, once we have the prefix-free encoding of the padded message, we take the sub key k0 and then we run our blockwise fully secure CBC, and whatever comes out as the output, that is taken as the overall outcome of the bitwise secure PRF F star under the key k for the message m. This is case 1 when my message is already, its length is, message length is already a multiple of the block size of the base PRF. Let us see how the things are handled for case 2. So, in case 2, imagine I have a message which has one full block of n bits, and the second block it does not have full n bits. So, again I have to do a padding here, but here I do not have to add a new complete dummy block, because it suffices for me to add 1 followed by the required number of zeros to ensure that I have the second block also have n bits. And then I use another sub key in this case, which I call as k sub 2, to do the prefix free encoding of the padded message, and then internally I invoke my blockwise fully secure PRF, which will now only have up to L number of blocks, because I will not be adding any dummy block in case 2 here, right, and whatever comes as an output, that is taken as the output of my PRF F star for the input m on the key k. So, these are the two cases here. Now, let us see how exactly the sub keys k sub 0, k sub 1, k sub 2 are derived. So, remember that the overall key for my PRF F star is just one key k of size n bits. So, the keys k0, k1, k2 are derived from the actual key k for the PRF F star by a sub key generation algorithm, which will be publicly known, and depending upon whether sender is in case 1 or is in case 2, it will derive the keys k0, k1, k2, but depending upon whether it is case 1 or case 2, it is either going to use k0, k1 or it is going to use k0, k2, right. Now, how the receiver is going to perform the operation? So, imagine a message and a corresponding tag is sent to the receiving end, and the receiver has to verify whether the message is the right, whether the tag T is the right tag on the message M or not. And imagine that the receiver also have the same key k. So, what the receiver is going to first do is this receiver is going to derive the sub keys k sub 0, k sub 1 and k sub 2, and then it has to remove the padding, right, because remember receiver has to first find out what exactly was the padding that sender has performed at its end. So, to remove the padding, what receiver is going to do is it can start parsing the message from the right position to the left position, and it can make a complete scan, and it can stop scanning as soon as it encounters the first one when it is scanning from right to left. As soon as it encounters the first one, that it knows that that is the padding which has been done, and it can remove and throw off the padding, and that can tell the receiver whether the receiver should operate as per case 1 or as per case 2. And I claim that this is an unambiguous padding, namely the receiver strategy of scanning the message from the right position to the left position and looking for the first occurrence of the 1 and stripping off the first occurrence of 1 followed by all subsequent zeros is indeed an unambiguous padding for the receiver, because if indeed we were in case 1, that means if sender has actually added a full dummy block, then indeed the first occurrence of 1 when receiver will do the scanning will be when it is done with the entire last block. Whereas, if the sender would have been in case 2, then the receivers, for the receiver, the first occurrence of the 1 will be in the last block itself, and that it knows that it is in case 2. So, once the receivers identify whether it is in case 1 or whether it is case 2, depending upon the required case, it can verify the tag part, verify the T part or the tag for the message that it has received, either by operating the PRF F star with the subkeys k sub 0, k sub 1, or with the subkeys k sub 0 and k sub 2, right. So, that brings me to the end of this lecture. What we have done in this lecture is we have seen how to construct message authentication codes for arbitrary long messages using fixed size PRF, and the approach for the construction is that we try to design secure PRFs which can take arbitrary bit string as input and give you a fixed size output. If we can construct such PRFs which can operate over arbitrary sequence of bits and gives you a fixed size output, then using such PRF we can easily get a message authentication code which can operate on bit strings as the input. And we have seen a candidate construction for a PRF operating on a sequence of bits, namely the CBC PRF, and we have seen several ways of constructing that CBC PRF. Namely, we have seen first how to construct a prefix-free blockwise PRF, prefix-free secure blockwise PRF, which is secure against a weaker adversary, and then by applying different mechanisms, namely encryption, deterministic prefix-free encoding, randomized prefix-free encoding, we convert that weaker form of PRF, namely which is secure only against a prefix-free secure adversary, into a fully secure PRF which is secure even against an adversary, which can make queries which does not constitute a prefix-free set. And then finally, we construct or convert this blockwise fully secure PRF into bitwise secure PRF using the CBC mode, right. So, now we have a tool for authenticating the messages and even to verify whether the received message has been received correctly or not. Namely, if we have a sender and a receiver who have a shared key k, and if we have a message authentication code which can give you a fixed size tag for arbitrary long messages, then to authenticate the message, sender can just compute a short or fixed length tag for that message, and along with the message the tag can be communicated to the receiver. When receiver receives that tag, and if the tag gets successfully verified with the key k, then that gives the guarantee to the receiver that it has originated from the same person who has the same key k with which the tag verification is successful. So, that is how the problem of authenticity and integrity are solved, right. I hope you enjoyed this lecture. Thank you.